Hello students, welcome back. I hope that you are keeping yourself very safe and also you are keeping yourself very much busy by watching these sessions. By that, I would feel that you are judiciously using the time during this pandemic, because the more you utilize the time right now, this is what is going to come back during the exam time. So going back to our session, in the last class we discussed about work. We discussed how to calculate work done by a constant force. We also discussed how to calculate work done when the force is a variable. Correct? Now let us move ahead. Today we will take up discussion on energy. So students, what is the meaning of energy? You have come across this word very frequently in daily life. Correct? Normally you say, I am not having that much energy. Sometimes, this is a statement which you come across. So what is the meaning of this word energy? See, energy is capacity of a body to do work, to perform work. So if a body has energy, then it can do work. It has the capacity to do work. Well, amount of energy possessed by the body is a measure of how much work the body can do. So that is exactly how energy and work, they are related to each other. The unit of energy is also same as the work, it is in joules. Now, this energy can be in many forms. This energy is in many forms. See, kinetic energy, potential energy. Then you have tidal energies, geothermal energies. Many forms of energy are there. But we will restrict our study to mechanical energy only. So we are discussing about mechanical energy. So what exactly we have in case of mechanical energy? So in mechanical energy, the first thing that we come across is known as kinetic energy. So what is kinetic energy? The word kinetic means motion. The word kinetic means motion. So energy possessed by a body by the virtue of its motion is known as kinetic energy. So kinetic energy is what? Energy possessed by a body by the virtue of its motion. So compulsorily motion, when a body is moving, so we say that it is possessing kinetic energy. So kinetic energy is energy possessed by a body by the virtue of its motion. If the body is not moving, this means it is not possessing any kinetic energy. Now question, this is the meaning, or this is what we can say as the definition for kinetic energy. How to measure kinetic energy? How to measure kinetic energy? So to measure kinetic energy, mathematically we say it is half mv square. This is how we measure mathematically kinetic energy. Now students, observe this. Kinetic energy we got as half mv square. Correct? Let us try to find the dimensional formula of kinetic energy. So this will be a revision of the chapter dimensional analysis as well. So kinetic energy, if I try to find the dimension, then what it will be? See, kinetic energy. So what we have? This kinetic energy can be taken as half mv square. So half constant will not have any dimension, dimensionless. Mass will be m. velocity is LT minus 1 and a square, so you will get this as m L to T power minus 2. This is the dimensional formula of kinetic energy. If you remember, the dimensional formula of work done is also the same thing. This means that work done and kinetic energy, they carry the same dimensional formula, they will have the same unit of measurement. Okay, that is exactly how we can find the dimensional formula of kinetic energy. Now let us move on. This is one form of energy. The other form of energy which we can say is known as potential energy. The other form of energy that we have is potential energy. So now, what is potential energy? Potential energy is the energy possessed by a body by the virtue of its position. So potential energy is energy possessed by a body by the virtue of its position. Position with respect to surface of earth. Because position we have to measure with respect to something. There has to be some reference. Without the reference, how to measure? So here the reference we are taking as the surface of earth. So potential energy is said to be the energy possessed by a body by the virtue of its position. See, it has to be, more clear. So different forms of potential energy are there. Potential energy can be in different forms. So if we see the different forms of potential energy, so potential energy, it can be gravitational potential energy. It can be gravitational potential energy. It can be elastic potential energy. It can be electrostatic potential energy. Different forms of energies are there, potential energies are there. That is why what we say is potential energy is the energy possessed by a body by the virtue of its position. Then it becomes gravitational potential energy. By the virtue of the arrangement, by the virtue of its configuration also we say potential energy of the system will be there. System of charges, then we say electrostatic potential energy. Right now we have to concentrate on gravitational potential energy and elastic potential energy. Only these two we have to see. So now let us see how to measure potential energy. So potential energy we say force, work done, work done. This is measured as mgh. This is gravitational potential energy. Gravitational potential energy is mgh. Now see, how did we get this mgh? Correct? We are saying potential energy is mgh. How did we get that? Kinetic energy we say it is half mv square. How did we get that? Very right, such questions should come to our mind. Now see, I'll show you how exactly we got potential energy. Here, we are lifting an object, surface of earth is there, and you are lifting a body. How much height did you lift above the surface of earth? H. What is the force that you applied? So the force that will be applied will be at least equal to the weight of the body. See, this is our reference. Now from here the body is placed. Now from here you will lift and take it to this position. Let us say this is height h. The weight is mg. M. So what is the force mg? Now in order to lift this body to this position, I have to apply a force which is at least equal to mg. Greater will definitely be good. But what is the minimum force required to lift this object? The minimum force required is mg. Minimum force. Now, what is the height that you are taking? H. So, what I can say? So, work done is, we know force into displacement, right? So, force mg, you are applying force in the upward direction, and h is also in the upward direction. So, this is mg is the force which you applied, and h is the height which you are taking. So, if, see here, please observe. If you take mg, that is weight of the body, then height is in the opposite direction, then theta is 180 degree. So work done by the gravitational force is minus mgh. Gravitational force is weight of the body, na? So mg is acting down, h is in the upward direction, so theta is 180 degree. So what we say is work done by the gravitational force is minus mgh. Work is negative. Now suppose the question is, what is the work done by the external agent? Now external agent is lifting the body. So the force is external force. This force here is external force. This external force F has to be greater than or equal to mg. Then only the body will lift. So the minimum is what? Mg. F is equal to mg. That is what we are using here. So what happens? External force, if I say, then it is in this direction. This is your F external force. And mg is the gravitational force. That is why, please understand this. So here I am getting it as mgh. This is the work done by the external force F. External agent. Now work done by the external agent will store in the body in the form of its potential energy. So this work done will be the potential energy. That is how we get potential energy as mgh. Students, please understand the inference that cos theta 1. Okay, so it all depends upon the direction of the force which you are considering and the displacement. Accordingly, we have to take the angle. So work done by the external agent here and work done by the gravitational force, they are two different things. That is what we get as potential energy. Now, what about kinetic energy? If you say kinetic energy, okay, fine. In that case, let us say kinetic energy. In kinetic energy, what we can say, work done. Again, the same thing, work done is force into displacement, we know. So force is mass into acceleration. A into S. We know the equation V square minus U square is 2AS. So if the body is starting from rest, U is 0. So AS can be written as V square by 2. So this is exactly how we get as half mv square. See here, students, observe there is V, velocity term there. That is why kinetic energy is related with energy possessed by a body by the virtue of its motion. So this work done is in the form of kinetic energy, we say. So that is exactly how we get the expression for the kinetic energy and potential energy. I guess the query that you had, how did we get these equations, is probably satisfied now. Fine. Let us proceed with the next topic, that we have elastic potential energy. So the question arises, what exactly is elastic potential energy? Where do we see elastic potential energy? How to calculate elastic potential energy? So students, to find elastic potential energy, now let us understand what is elastic potential energy. So, elastic potential energy. This energy is possessed by springs. This we see in springs. Springs. Normally in the pen also you find small spring will be there. In the vehicles you find them as by the name of shock absorbers, we say springs. So the concept in spring is F, force. See, when we apply force on a spring, see this way. When you apply force on the spring, it compresses, you are compressing. The moment you release it, it comes back to the original state. What does that mean? What information we get from that? It means that when you are compressing a spring, you are applying a compressive force. Then there is a force generated in the spring which is trying to restore the original natural length of the spring. That force is called restoring force. See, the name only suggests restoring. This force has a tendency to restore the original natural unstretched length of the spring. So now if the same thing happens if you stretch it. If you stretch it, if you apply a stretching force on the spring, the moment you release the stretching external force, the spring comes back to the original length. See, so this means that in a spring, if you compress or you stretch, there is a restoring force coming into play which tries to restore the original or the natural or the unstretched length of the spring. If you compress it, the restoring force tries to act in the outward direction to take it to the original length. If you stretch it, the restoring force acts in the inward direction, which means it acts in a direction opposite to the extension or the compression which you are giving to the spring. What is the meaning? It means suppose you have a spring of this length, you compressed it, so you made it this way, na? So the force is acting in the upward direction. And what is the direction of compression? You gave, see, force. So the restoring force always acts in a direction opposite to whatever extension or compression you are giving to the spring. And that is why this force is written as proportional to minus x. Minus refers to the fact that the restoring force and the extension, they are in opposite direction. This F is restoring force. And this X is extension. It can be compression also, huh? It can be. Now if you take F then proportional to X, then this force F is applied force. See, the minus sign is not there. If you stretch it, stretching force will stretch, elongate the spring. Compressive force will compress the spring. So direction of the external force and the movement of the spring will be in the same direction. That is why we don't have a minus sign here. In any case, whichever one you take, what we can say is F is equal to minus of K into X. K is the constant of proportionality which is known as spring constant. It is known as spring constant. Same way here also, F will be equal to a constant of proportionality into X. This is how we can estimate what is the force acting on the spring. From the force we can find out work done. See, the force is a variable force. Force is a variable force. See? So, what will be the work done? Now, work done we have to find. Work done, dW is equal to, we know, F dx. In case of variable force, work done by a variable force, we have seen that. If you remember, in key points we had discussed this in the last class. F is kx dx. So this is your dW. So total work done, W is integration of dW. So k integration of x dx, let us say from 0 to x. So what we get? This as half k x square. This work done stores in the spring in the form. This is the work done by the external force. So work done by the external force stores in the system in the form of its potential energy. Which potential energy? Elastic potential energy. So this is what we can say as the magnitude of elastic potential energy that gets stored in a spring, half kx square. You can write kx as f. So you can write it as half of f into x. Different formats we can have, but this is exactly how we can find the elastic potential energy. So students, you have to write these derivations yourself once and try to get the feel of how we are getting it. Okay? Yes. Now, after seeing the two forms of energy, now let us go to the next topic, that is so the next topic is law of conservation of energy. This is known to you, but then we have to establish this with respect to the mechanical energy possessed by the body. For that I am taking one situation. See, this point, let us say it is A, this point, let us say it is B, and this is ground, let us say it is C. So what I am trying to say here is, an object is released from A. An object is released from A. Observe here. So if it is released from A, we know U will be 0 here, free fall, and A will be plus G, we can say. This is what we have. So now, let us say this distance is x, A to B, and from A to C, this is h. This is what we have. Now, with this as our reference, let us try to find out energies at all the points A, B, and C. So first, at A, what will be the kinetic energy at A? That is half m v square, but velocity is 0, so kinetic energy is at A is 0. Clear? Now let us try to find potential energy. So potential energy at A will be what? mgh. This is what we have. Therefore, total energy at A is kinetic energy at A plus potential energy at A. This is total energy at A, mechanical energy. So kinetic energy is 0, this is mgh. So what we get? Total energy at A is mgh. This is what we get. Correct? Now let us do the same thing for the second case, that is at B. At B, what it will be? This is where you have to concentrate. At B, kinetic energy at B will be half m, whatever is the velocity at B, square of it. Now what will be the velocity at B? Please follow this. What we see is at B exactly, see here, U is 0, A is G. So what I can say at this point, velocity at B, so V square minus U square to AS, so VB square, this is 0 to GX. So VB square is 2GX. So this will give us half m 2GX. So kinetic energy at B is 2 cancels out, mgx. This is kinetic energy at B. Similarly, what will be the potential energy at B? Potential energy at B will be mg. What is its position with respect to ground? Observe, B is at a height of h minus x. It is h minus x. So what we get? This is the potential energy of the body at B. Therefore, what will be total energy at B? Total energy at B is kinetic energy at B plus potential energy at B. So kinetic energy at B is mgx. Potential energy at B is mgh minus x. So this gives us again mgh. See, please concentrate. This is exactly what we are getting. Now observe, kinetic energy at A is 0. Potential energy at A is this, mgh. Now kinetic energy at B is mg into x. So kinetic energy increased. Please observe, kinetic energy increased from 0 to mgx. Now what is happening to potential energy? Potential energy at A is mgh. Now potential energy at B became mgh minus mgx. Please see this. This is mgh minus of mgx, which means that the potential energy at B decreased by an amount mgx. Potential energy at B decreased with respect to the potential energy at A by an amount mgx. Now see, correlate. Whatever is the decrease, that was the increase in kinetic energy. So what can we say? Decrease in potential energy is equal to increase in kinetic energy. Reverse is also true. So see, total energy is constant, which means that if kinetic energy is increasing, corresponding potential energy is decreasing. That is why total energy is a constant. That is how we can say that energy is conserved. To confirm this, let us verify what happens at C. So at C also we have to find out. So let us say at C, if we try to find out, here only we will find at C. What will be the kinetic energy at C? Same thing, half mv c square. Please try to understand the subscripts that I am using, because this will give you a better understanding of what that term is. You don't have to every time worry what that represents. Okay, velocity at C, that's all. Now at C, what will be the velocity? Now at C, if you try to find the velocity, we will use the same logic where we have used v square minus u square. See, v square minus u square is 2as. V at C square, it is falling freely, so u is 0. So this is 2gh. So what we can say, vc square is 2gh. This is what we get. So if I substitute here, what we are getting, if I substitute this, I will get as half m and 2gh we get. So we are getting, therefore kinetic energy at C is mgh. Now, what will be the potential energy at C? Can you tell me what is the potential energy at C? Potential energy at C. In order to find potential energy at any point, what did we see? Its height with respect to the surface of Earth. So what is the position of C with respect to surface of Earth? It is on the surface of Earth. Therefore, H is 0, so potential energy becomes 0. If potential energy is 0, so what can you say about the total energy at C? That is again mgh. See how we can show. This is exactly what is law of conservation of energy. It states that the total energy of the system will remain constant. That is what we say, conserved. So what happens? The energy transforms from one form to another form. That is to say, it is converting from kinetic form to potential form and vice versa. Like say for example, when you take an object and you throw it up, you imparted initial velocity to it. So you gave initial kinetic energy to it. So it started moving up. But gravity is pulling it down. Na? So its kinetic energy is getting consumed in overcoming the gravitational pull. So after traveling some height, it comes to rest, which means it lost all its kinetic energy. So when it lost all its kinetic energy, it gained height above the surface of Earth. Na? So there is a gain in potential energy. See, that is exactly what we see in daily life also. It gains certain height. At that point, it has potential energy which is mgh, and the kinetic energy which it had possessed, half mv square, entirely got converted to mgh, provided we don't consider air resistance. Some energy will be lost because of air resistance. If we neglect those things, then half mv square is the kinetic energy which you imparted. Because of the loss in kinetic energy, there was a gain in potential energy, and gain in potential energy means it gained height above the surface of Earth, and that is exactly how we can compute. So this is what is law of conservation of energy. Now let us try to understand work energy principle, work energy theorem. This is a very important theorem. Let us try to understand. See, work is there and energy is there. Now how to correlate work and energy? Now, work done is, we know F into S. Na? This is what we say for a constant force. If it is a variable force, we say dW is equal to F dx. This is what we can say. Now F, we can write it as m into A into dx. Now A, this can be written as dV by dt and dx. We can write this way, because acceleration is rate of change of velocity. Now please observe, this dx by dt can be written as v. So we get this as mv dv. So we get dw as mv dv. Now w will be what? Integration of dw. So this will give us what? M integration of v dv from initial velocity u to final velocity v. So now what we get? So therefore we can say w is equal to m integration of v is what? V square by 2. What are the limits from u to v? These are the limits. So substitute the limits. What we get? M v square by 2 minus u square by 2. So what we get? This as half mv square minus half mu square. And what it is? This thing is nothing but this is final kinetic energy minus this is what? Initial kinetic energy. So what we are getting? So from this we conclude work done is change in kinetic energy. That is exactly what we can write. See, this thing, so W is equal to M, integration of V is V square by 2, limits are from U to V. So this is M into V square by 2 minus U square by 2. So this is nothing but half M V square minus half M U square. So this is what? Final kinetic energy minus this is initial kinetic energy. So we can say work done is change in kinetic energy. This is work energy principle. It states that the work that a body can do is equal to change in the kinetic energy of the body. Now the question arises, can we say that it is only for kinetic energy? No. We can also use the same thing for potential case, position case. See here, for if I use the same thing, work done is F into S, what we have used. This I can say dW is equal to F dx. If I want to use potential, then the external force will be equal to the weight of the body that we have seen. The external force should be equal to. External force can be greater than, but the minimum force required is weight of the body. So that I will take it as mg and dx. This is dw. So w is equal to what? Integration of dw. So that is mg will come outside the integral sign and we get dx. This I will say from initial h1 to final position h2. So what we get this as mg. We get h2 minus h1. This is w. This work done, see mg h2 final minus initial, again change in potential energy. Please understand, it will be in opposite direction. Always loss in potential energy is equal to gain in kinetic energy. Both cannot be loss. If kinetic energy increases, potential energy has to decrease. If you are moving against the gravity, see, final, initial, that is exactly what we can say. Final potential energy minus initial potential energy. But if you take it as a loss, then it will be initial potential energy minus final potential energy. So this will be equal to final kinetic energy minus initial. See, this is change, which is nothing but decrease. So loss in kinetic energy is equal to, so what we can conclude? We can conclude that work done is change in potential energy. It is also equal to change in kinetic energy. But students, please understand it. Loss in potential energy will be equal to gain in kinetic energy. Loss in potential energy can never be equal to loss in kinetic. Both cannot be loss, both cannot be gain, because law of conservation of energy has to hold true. This means that if kinetic energy increases, potential energy has to decrease. If kinetic energy decreases, potential energy has to increase. Like, see, as I gave you the example, if you drop a body, height is with respect to surface of earth is decreasing, potential energy is decreasing, kinetic energy is increasing, its velocity is increasing continuously. Now if you throw the body up, kinetic energy is decreasing because it is gaining potential above the surface of earth, it is gaining height, so it is gaining potential energy. So the potential energy gain is equal to loss in kinetic energy. So that is exactly what you have to always remember. gain in kinetic energy is equal to loss in potential energy. This is, and each of them is equal to work done. Reverse is also true. Loss in kinetic energy is equal to gain in potential energy is also true. That is exactly how we can correlate work done, capacity to do work done, to do work, and kinetic energy, then work and potential energy. That is exactly how we can correlate. So that is exactly how work done can be found out. Now students, let us discuss about the next term, that is power. We have discussed what is the meaning of the term work. We have discussed what exactly is energy. Now let us take what is the meaning of power. Power is rate of consumption of energy. What is the rate at which energy is consumed by a body? That is called power. Now rate means what? Time. So we can say this as energy consumed upon time taken. This is what is power. Energy consumed upon time taken. Just now we saw that energy is equivalent to work done by the body. So this also we can write work done by time taken. See, these are the different forms in which the same physical quantity power can be expressed. Now, work done is what? Force into displacement by time. Now, what is displacement by time? This displacement by time is what? Velocity. So, what we can say? Therefore, power P is equal to F dot V. See, this is exactly how we can write the relationship between force and velocity to get power. It can also be written as work done and time taken if we know energy. So these are the different formats in which power can be expressed. So now what is the unit of power? Work done. What is the unit of energy or work done? Joule. What is the unit of time? Second. So that is, so the unit SI unit of power is watts. So it can also be said as joule per second. Normally we come across one more unit that is said to be 1 kilowatt hour. This is the unit of watt physical quantity if we want to find out. Let us try this. 1 kilowatt hour. See, this I can write as 1. Kilo is 10 power 3. Watt is joule per second. And 1 hour, 60 minutes into 60 seconds. So what we get now? This second and this second cancels out. So what we get finally? 3600 into 10 power 3 joule. Now what physical quantity is measured in joules? Work done or energy. So 1 kilowatt hour is the unit of energy. So this can also be written as 3.6 into 10 power 6 joule. So 1 kilowatt hour is 3.6 into 10 power 6 joule. So this is exactly how we can say this 1 kilowatt hour represents the electrical unit. One electrical unit is this much. So if this much of energy is consumed it is equivalent to 1 unit of electric energy. That is exactly what we have. Next term that we have here after power is efficiency. Efficiency is the next term. So, what is efficiency? Where exactly are we using this term called efficiency? Efficiency tells us when energy is transformed, how much effective that transformation of energy is. Whether entire energy got transformed or some part of the energy was lost. That some part of the energy which we say lost is the measure of efficiency of the system. So efficiency is said to be output upon input. If you want it in percentage, multiply by 100. Output. Here any system, what is the output? Output is work done. And input is energy supplied. This will give you efficiency. So efficiency is work done, because like say for example we are using any machine. Efficiency, you give electrical energy to it. That is your energy supplied. You are giving electrical energy to it. And the result is what? We are getting work done, mechanical work. Like say in two-wheelers, you put fuel into it. And because of that it is traveling some distance. So the distance which it is covering will be called as the output work done. And input is what energy you have given. That is exactly how we are able to measure the efficiency of any system. Remember, efficiency will be less than 1. When you multiply it with 100, then only you will get it in percentage. That is how efficiency is calculated. Well student, let us take one numerical. The question reads like this. If the linear momentum of a body is increased by 50%, then by what percentage will its kinetic energy increase? So how to solve this question? We need relationship between linear momentum and kinetic energy. Now, kinetic energy is half mv square. It is known to us. Now see, we have to write this in terms of linear momentum. See, we can write this way, divide by m here and multiply by m here. So m square v square we get. What is linear momentum? Mass into velocity. So here what we are getting? This we are getting p square upon 2m. This is the relation between kinetic energy and momentum. Students, you can always remember this, or you can remember the method by which we are arriving at it. One step only. Now, let us go to the question. It says linear momentum of a body is increased by 50%. So, if P1 is P, P2 will be how much? 50% increased P plus 50% of P. So that is P plus P by 2. So P2 is equal to 3 by 2P. We got P1, we got P2. By what percentage kinetic energy changes? So using this equation, we can say K2 by K1 is equal to P2 square by P1 square. So from this we can say K2 by K1 is equal to P2 square. So it is 1.5 P upon P whole square. So this gives us how much? 2.25. This is what we got. K2 by K1. So come to this, we got K2 is equal to 2.25 K1. We want percentage change. So K2 minus K1 is 1.25 K1. So K2 minus K1 by K1 is 1.25. I want percentage change. Multiply by 100 on both sides. K2 minus K1 by K1 into 100 will be 125%. This is exactly how we can find out what is the percentage change in kinetic energy. Now the change can be increase, can be decrease. So see here, kinetic energy is directly related to the momentum, which means that if kinetic energy increases, momentum also increases. Kinetic energy decreases, momentum decreases. So here we can say 125% increase. That is verified in the question. That is exactly how we can find out the relationship between kinetic energy and momentum, and we can conclude what exactly is happening. See, please remember, this is the method which is to be used whenever the percentage change is very high. When the percentage change is small, we cannot use this method. We have to go for approximation method. Well students, let us take one more problem. This problem is similar to what we did in the previous problem, but carefully observe the data. Here I have reversed. There we found out momentum and kinetic energy. Here it is kinetic energy is given. If the kinetic energy increases by 3%, find the percentage change in its linear momentum. Okay, so we know kinetic energy is half mv square. Again I am writing the same steps. So this can be written as half m square v square. So I can say kinetic energy is related as p square by 2m. Now, what is given? Kinetic energy increases by 3% is given. So please observe student, this percentage is given very small, 3%. In the previous question you see it is given 50%. So we went for one particular method. Now here carefully observe, I am using approximation method. Delta K by K is equal to 2 times delta P by P. See, you have done this in error analysis. How to calculate fractional error, how to calculate percentage error. That analysis I am taking. Delta K by K is equal to 2 into delta P by P. Now if I want in percentage, I can write it as delta K by K into 100 is 2 times delta P by P into 100. Now the question says if the kinetic energy increases by 3%, so this is 3%. This is equal to 2 times delta P by P into 100. So what we get from this, delta P by P into 100 is 1.5%. So the change in momentum is 1.5%. See, these are the two methods by which you are supposed to solve. Please concentrate on the data which is given. If this percentage change is large, go for the normal algebraic method. If the percentage change is small, whether it is kinetic energy or momentum, it is not important, but the percentage change is more important. If it is small, then go for approximation method and get the answer this way.